In category theory, a branch of mathematics, the functors between two given categories form a category, where the objects are the functors and the morphisms are natural transformations between the functors. Functor categories are of interest for two main reasons. Many commonly occurring categories are functor categories, so any statement proved for general functor categories is widely applicable. Every category embeds in a functor category. The functor category often has nicer properties than the original category, allowing certain operations that were not available in the original setting. Definition: suppose C is a small category and D is an arbitrary category. The category of functors from C to D, written as functor.DC, has as objects the covariant functors from C to D, and as morphisms the natural transformations between such functors. Note that natural transformations can be composed if mu Fg is a natural transformation from the functor f CD to the functor g CD, and eta GH is a natural transformation from the functor g to the functor h, then the collection eta mu FH defines a natural transformation from f to h. With this composition of natural transformations, DC satisfies the axioms of a category. In a completely analogous way, one can also consider the category of all contravariant functors from C to D. We write this as funct. If C and D are both pre-additive categories, then we can consider the category of all additive functors from C to D, denoted by add. Examples: if I is a small discrete category, then a functor from I to C essentially consists of a family of objects of C, indexed by I. The functor category Ci can be identified with the corresponding product category. Its elements are families of objects in C, and its morphisms are families of morphisms in C. A narrow category is just where 2 is the category with two objects and their identity morphisms, as well as an arrow from one object to the other. A directed graph consists of a set of arrows and a set of vertices, and two functions from the arrow set to the vertex set, specifying each arrow's start and end vertex. The category of all directed graphs is thus nothing but the functor category SETC, where C is the category with two objects connected by two morphisms, and set denotes the category of sets. Any group G can be considered as a one-object category in which every morphism is invertible. The category of all D sets is the same as the functor category SETG. Similar to the previous example, the category of K-linear representations of the group G is the same as the functor category KVECTG. Any ring R can be considered as a one-object pre-additive category. The category of left modules over R is the same as the additive functor category, add, and the category of right R modules is add. Because of this example, for any pre-additive category C, the category add is sometimes called the category of left modules over C, and add is the category of right modules over C. The category of Price-Hebes on a topological space X is a functor category. We turn the topological space into a category C having the open sets in X as objects and a single morphism from U to V if and only if U is contained in V. The category of Price-Hebes of sets on X is then the same as the category of contravariant functors from C to set. Because of this example, the category funct is sometimes called the category of Price-Hebes of sets on C, even for general categories C not arising from a topological space. To define sheaves on a general category C, one needs more structure, a graph and deep topology on C. Facts. Most constructions that can be carried out in D can also be carried out in DC by performing them component-wise, separately for each object in C. For instance, if any two objects X and Y in D have a product X times Y, then any two functors F and G in DC have a product F times G, defined by equals F times G for every object C in C. Similarly, if A to C, Fg is a natural transformation and each eta C has a kernel Kc in the category D. Then the kernel of eta in the functor category Dc is the functor K with K equals Kc for every object C in C. As a consequence, we have the general rule of thumb that the functor category Dc shares most of the nice properties of D. If D is complete, then so is Dc. If D is an abelian category, then so is Dc. We also have, if C is any small category, then the category SETC of Priestheves is a topos. So from the above examples, we can conclude right away that the categories of directed graphs, G-sets and Priestheves on a topological space are all complete and co-complete topoi, and that the categories of representations of G modules over the ring R, and Priestheves of abelian groups on a topological space X are all abelian, complete and co-complete. The embedding of the category C in a functor category that was mentioned earlier uses the Yonnet dilemma as its main tool. For every object X of C, let Hom be the contravariant representable functor from C to set. The Yonnet dilemma states that the assignment is a full embedding of the category C into the category funct. So C naturally sits inside a topos. The same can be carried out for any pre-additive category C. Yonnet then yields a full embedding of C into the functor category Add. So C naturally sits inside an abelian category. The intuition mentioned above can be made precise in several ways. The most succinct formulation uses the language of adjoint functors. Every functor f D induces a functor fc. DCEC. If f and g is a pair of adjoint functors, then fc and gc is also a pair of adjoint functors. The functor category DC has all the formal properties of an exponential object. In particular, the functors from E times CD stand in a natural one-to-one correspondence with the functors from E to DC. The category cat of all small categories with functors as morphisms is therefore a Cartesian closed category.